Okay, so now let me try to say a little bit more about smooth functions. Okay, on particular on a manifold, right? So let M be a d-dimensional, sort of a smooth d-dimensional manifold. And what that basically means is that M has an atlas of charts coordinate charts, which give you a local diffeomorphism from a neighborhood of M, it's like to an open ball in RD, which are sort of diffeomorphisms. Actually, it should say they are homeomorphisms. Neighborhood of M to an open ball, right, in RD. Okay. And then technically it's like what one means, it's like when we talk about smooth manifolds is that that's the what is called the change of coordinates map. Okay, so you have, it's like a manifold M, right, and you have, say, two coordinate patches, okay, one of which maps to an open ball in RD, and another one maps to another open ball in RD. They have an overlap region, right? And so you can define, it's like a map from RD, or some neighborhood of RD to some neighborhood of RD, right? Using, it's like these diffeomorphisms, okay? And the basic idea then is that if you have a smooth manifold, then these, what are called change of coordinate maps from some open set in RD to another open set in RD, they have all their derivatives, okay? So for us to have a smooth manifold, right, all the change of coordinate charts, the change of coordinate maps have sort of all their derivatives. So all their derivatives exist, okay? And then that's technically what one means by smooth. It's like in practice, it's like for most of the discussions we have, we don't actually need smoothness. We just really need sort of the first and second derivatives, it's like, to exist, right? So practically, we just need sort of the first and second derivatives to exist. Okay, all right. Anyhow, all right. So now let's say that you have okay. So all right. So I guess the other thing I should say is that there's this idea of the tangent space, right? So the tangent space. So it's denoted TXM. It's the set of tangent vectors to M, right, which are sort of based at x, which is a point on the manifold M. Okay, so I'm not going to go too much into the details about this, but at least it's like when you're setting, it's like where you have an embedded manifold, which is a manifold which is, say, it's like embedded, it's like into some high dimensional space, then the usual notion of tangent vectors sort of applies here. Okay, and of course, if you know a little bit more about manifold theory, it's like then it's not necessary for you to do embeddings. It's possible to define the tangent spaces intrinsically in a variety of ways. But again, it's you know, that's something which isn't so critical at this point. Okay, so all right. So now it's like let's talk about a smooth mapping from one manifold to the other. So let's say if an f from m to n, right? Okay, so this and this is smooth, right? Then the claim is that this induces a linear map between tangent spaces. Okay, which is just the derivative, right? Okay, so it's denoted d of f. Okay, and then usually you specify the point where you evaluated the fx. Okay, so this is a map from the tangent space at x to m to the tangent space at f of x to n. Okay, all right, and then in practice for this section, right, we are primarily concerned with the case where n is just the reals. Okay. All right. So now you have a linear map. So now you just have df of x as a map from txm to tf of x at the reals. Okay, and then of course it's like the tangent space to a vector space at a particular point can be identified at the vector space itself. So this looks like a copy of the reals, more or less. Okay. All right. So so this is a linear map, right? So the image. Okay. So this thing here is isomorphic to R. Okay. All right. Let me just maybe put that parentheses here. Okay. All right. The whole thing here is just isomorphic to R, right? So since this derivative map is a linear map, right? The image. So since df of x is a linear map, right? The image of such a map is either the entire real line or 0. Okay. All right. So that then allows us to say something about this notion of regularity. Okay. So we call the point x on the manifold, right, a regular point. If of f, right, if df at the point x, right, is surjective, and then so that means that it's onto, that means the image of df at the point x is just the entire real line, right, and we call x a critical point right, if the image is 0, right, if the f of x is the 0 map. Okay. All right. So that sort of introduces this idea of distinguishing. It's like points in a particular way. So one way to sort of see this is that, okay, so I should say the following. Okay, so again, you have this manifold M, right? And you can imagine having a coordinate chart which maps it to RD, right? And then you have a map F to the rails. Okay, so you can look at the coordinate representative of this, right? So you can, let's look at what it's called F tilde. So F tilde, right, is just defined to be what you want, of course, is you want to go from here to here. So let's label that map. Okay, so you take the inverse of the coordinate map, you compose it with F, right? Then this is now a map from RD, or at least some subset of RD, to the rails. Okay, and then you can write down, you know, it's like the coordinates associated with this, right? So in any case, so the basic idea then is that you can characterize, if you will, it's like critical points. So a critical point, right, satisfies the property that if you take the partial of this local coordinate representative with respect to, say, x1 evaluated x, that's equal to x2 at x all the way up to, so there's a d-dimensional space, right, xd at x, and that's equal to 0. Okay, so that means all the partial derivatives, it's like of the local coordinate representative of the function f, right, vanish. Okay, so all the sort of first partial derivatives sort of vanish. Okay, so this is how you characterize a critical point in local coordinates. Okay, and the point, if you will, is that so I said that f, it's like composed with sort of the inverse of the coordinate chart. It's like satisfies this property, and then the point, the point is that if you were to write this in a different coordinate chart, then the fact that the change of coordinates is infinitely differentiable in sort of both the forward and the backward direction basically means that this thing has full rank. Okay. So the map from RD to itself, it's like has full rank. So you know, this characterization, it's like which I've done in terms of a particular coordinate chart, is independent of the choice of coordinates. Okay. So the remark is that sort of this characterization right of sort of critical points is independent of the choice of coordinates. Okay, and that's because so this is because of the chain rule, and the fact that change of coordinates map sort of is sort of invertible, amongst other things. Okay, all right. Okay, so we talked about this idea of a critical point. Okay, so critical point x, right? And then, of course, if you remember, it's like we had defined this function. It's like in the manifold. So you can ask what is the function value associated with a critical point. So, so given a critical point x on the manifold, right? The image of x is f of x, which is a critical value. Okay, of the function f. Okay. All right, and then all the other values are regular. So all non-critical values are regular values. Okay. All right. So I mentioned that in practice, it's like for the purposes of a discussion of Morse functions, we only really need that your coordinate chart, it's like has sort of change of coordinates. It's like which are at least twice differentiable, and the reason for this is because in addition to computing the first partial derivatives, you also can compute the second derivatives to form the Hessian of the function f. Okay, so let's go ahead and do that. All right. So the Hessian, right, is really just this matrix of second derivatives of f at x, right, is the matrix of second derivatives. And as before, it's like when we first talk about first derivatives, this technically means that you have to find a local coordinate representative of the function f. It's like using a coordinate chart. I'm just going to suppress that, but again, you should understand that whenever you're actually writing these coordinate expressions, you're always doing this on a local coordinate chart. Okay, so you have the second derivative of f respect to x1, x1, all right, d squared f d x1 dxd, then d squared f dxd dx1, then d squared f dxd dxd. Okay, and then all of them are evaluated at x. So I'm just going to sort of denote that. It's like by doing the evaluation at the end. It's like as opposed to each individual entry. Okay. So we talk about critical points. It's like, and that again has to do with whether or not the image of the function, image of the linearization of the function is the whole real line or just 0, right? And then if you happen to be at a critical point, then we can say something more about the type of critical point you have. So critical point x, right, is non-degenerate. Okay, if the Hessian is non-singular. That is to say that the determinant of h of x is not equal to 0. Okay, And again, as before, this doesn't depend on coordinates, right? So this does not depend on the choice of coordinates. And again, more or less, this has to do with the fact that the Jacobian associated with the change of coordinate charts, which will show up if you want to, relate the Hessian evaluated in one coordinate representation to the Hessian related to another coordinate representation, that is going to have non-zero determinant. Okay, yeah. So, so so in any case, the bottom line, if you will, it's like the determinant of the Hessian. It's like in whether or not it's zero or non-zero is independent, again, of the choice of coordinates. Okay. All right. So all right. So anyway, so now it's like with this notion on degeneracy, it's like we can then say a little bit about what we want these nice functions in segment manifolds to be, and this leads to the idea of Morse functions, which we'll talk about in a little bit.